Hello everyone, welcome back to Daily King's Huts. Today we'll be taking a look at the last major contest of this year, which is the Putnam 2023. We'll be going over the first 4 problems, and some comment that the first few problems are either too easy or difficult for really strange reasons. So without further ado, let us take a look at the first 4 problems of Putnam 2023. So for the first problem, we have the following. For a positive integer n, let fn be defined by cosine x, cosine 2x, dot until cosine nx. Find the smallest n such that f double prime n evaluated at 0 has absolute value bigger than 2023. Okay, this problem is actually not too difficult, so if you'd like to give it a go, feel free to pause the video and try it out yourself. But if you are just here to enjoy the solution, let us now go through the problem. So the solution involves just differentiating fn and see what happens. So if we differentiate fn, we can just apply the product rule, which will then differentiate one factor at a time. So if I differentiate fn, the first factor I'll get, or rather the first term I'll get is by differentiating the first factor, which is minus sine. And then the second term I'll get is by differentiating the second factor, which is minus 2 sine 2x, and so on until I have minus n sine nx here, highlighted in yellow. Okay, then now I just want to differentiate again to find fn double prime. But to make my notation life easier, I'm going to just evaluate it at 0 directly and see what happens. Okay, so if I differentiate f prime again, I will be differentiating term by term. Okay, so for the first term, I apply the product rule. What happens? I'll get a whole bunch of new terms, but notice that if I use the product rule and I'm differentiating one of the cosine terms, then sine x would survive, and if I evaluate at 0, I'll get sine 0, which is 0. So the parts of the product rule where I differentiate a cosine factor will all evaluate to 0, and only the term where I differentiate sine x will survive. So the first term after using product rule and evaluating at 0 will give minus cosine 0, cosine 2 0, and so on until cosine n 0. All the other terms will die because of the sine x evaluate to sine 0. Similarly, for the second term, if I am differentiating under the product rule, if I'm differentiating one of the white color terms, I would end up having sine 2x survive and sine 0 is 0. So the only term that survives after I evaluate at 0 is if I differentiate the yellow term. So I will get minus 2 square, cosine 0, cosine 2 0, and so on until cosine n 0. So this rule applies all the way until including the last term. So if I use the product rule, same thing. Only the part of the product rule where I differentiate the yellow term would survive. So I'll get minus n squared times all these cosine terms in this case. And cosine of 0 is 1, so over here this all evaluates to minus 1 square, minus 2 square, and so on until minus n squared. So in summary, this problem becomes, we want to find the smallest n such that the sum of the first n squares is bigger than 2023. And from here you can directly compute that the answer is n equals to 18. So I hope you enjoyed problem 1. I would say this is quite straightforward and easier than usual because most people would just try and differentiate and see what happens. So there's nothing much to it, and hope you still enjoyed this problem nonetheless. Let's take a look at the next problem. So over here we have problem A2, which is an algebra problem. Let n be an even positive integer. Let p be a monic real polynomial of degree 2n. So basically, px is just this polynomial over here, where it's monic degree 2n, and all these coefficients are real coefficients, okay? Suppose that p of 1 over k is equals to k squared for all integers k such that k is plus minus 1, plus minus 2 until plus minus n. Find all other real numbers x for which p of 1 over x equals x squared. So this problem is actually quite a neat little algebra problem. I would say it's something that has a same flavor as IMO problem 1 or problem 4. Or easy problem 2. So if you would like to give this problem a go yourself, feel free to pause the video and try it out yourself. Okay, let's begin solving this problem. The key expression of interest to us is basically p1 over x equals x squared. So let's take a look at p1 over x minus x squared. Basically, the solutions to this equation would be solutions that cause this to evaluate to 0. So let's sub in 1 over x and see what happens. So you sub in 1 over x, you get this expression over here. Not too complicated to write out, but it's quite ugly. I don't want to be dealing with fractions like this. I want to be dealing with polynomials. So I will take out the common factor of 1 over x to the 2n, and now I have a nice little looking polynomial here. So I'm going to define gx to be this polynomial here, except I took the negative of it so that I have a positive leading coefficient. And why do I want to deal with this polynomial instead? Well, basically, I haven't really made the problem any different. This is an equivalent problem. Now, if x is a solution to this equation over here, basically x will cause this to evaluate to 0, and so x will cause this to evaluate to 0, so x will be a root of gx. And conversely, if x is a root of gx, well, firstly, we check that x cannot be 0, because x equals 0 doesn't give a root. So I can very safely put in x into this equation here without worrying that I have 1 over 0. So I put the x into this equation. Indeed, this part evaluates to 0, so this thing evaluates to 0, so x is also a solution to this. So in essence, I've converted the problem involving this equation into a problem about finding the roots of this polynomial over here. And working with polynomial is a lot better because we know a lot of facts about polynomials, right? For one thing, we know that this polynomial will have 2n plus 2 roots. And we already know 2n of the roots because we are told that all values of k equals to plus minus 1 plus minus 2 under plus minus n satisfy this equation. So it says it's a root of g. Now, what we are interested in is to find the two remaining roots, alpha and beta. So this is what the question comes down to. Find these two remaining roots of g. And to do this is actually not too difficult. We are just going to apply beta's formula. So looking at the second coefficient over here, which is 0, we know that the sum of the roots will be equal to 0. So alpha and beta are negative of each other. Looking at the constant term, we know that the product of roots is going to be minus 1. And so the product of all these roots will be minus 1. What's the product of all these roots? Well, n is an even number, so there's an even number of negative terms. So all the negative terms also multiply to positive n factorial. So what we have is n factorial square alpha beta equals minus 1. And from here, alpha beta is minus 1 over n factorial square. And since alpha beta are negative of each other, basically the two remaining roots are plus minus 1 over n factorial. So that's all to problem A2. I hope you enjoyed this problem. It's really interesting and it's a neat little problem. I would say it's easier than usual for Putnam A2, but nonetheless, I appreciate the beauty of this problem. So let us now take a look at problem A3, which is where the fun really begins. So for problem A3, we need to determine the smallest positive real number r, such that there exist differentiable functions f and g satisfying a whole bunch of conditions. f0 bigger than 0, g0 equals 0, mod f prime less than equal to mod g for all x, mod g prime less than equal to mod f for all x, and fr equals to 0. So this is a lot to take in. So I will begin by giving you a motivational speech in order to understand what all these conditions are talking about and what is the crux of this problem. Okay, so basically you have your x and y axis here, okay? And you have two functions f and g. f0 is bigger than 0, g0 equals 0. Okay, and the point of this question is you want to find the smallest r such that this function f and g, but then the key condition here is fr equals to 0. So you want f to come down to 0 And because you want R to be as small as possible, you want your f to come down to 0 as fast as possible, right? So that R can be as small as possible. But the problem is the rate at which f can come down is basically f prime, and that is bounded by the value of g. So you see the problem here is g starts at 0. So at the beginning, f cannot really come down quickly. It has to have a slope of 0. But as g increase, you can have f start coming down. Now, how fast can g increase? You want g to be huge so that f can come down very quickly. But the problem is g cannot increase quickly because g prime is also bounded by f. Right? So at the start, okay, I can increase based on what the value of f is. Now, the other problem is as g increase, fine, f can start to come down. But as f starts to come down, g can only increase slower and slower because of this inequality here. So you also cannot have like f suddenly like boom come down to 0 straight away. So that is where the tension in this problem lies. All these conditions have a tension of preventing f from coming down like super rapidly, and you want to find the smallest value of r such that you can have fr equals to 0. So if you think about it, as I mentioned earlier, at the start f cannot come down very quickly, but as the value of g increases, f can start coming down faster and faster, but g can only increase slower and slower. So the shape of the graph that seems to give the optimal solution might look something like this. And this is where you might guess that the optimal solution is actually r equals pi over 2, which is achievable with f equals cosine and g equals sine. So you can indeed check that this pair of solutions satisfy all these conditions. And r equals pi over 2 is basically achieved with this set of solutions. Now, we have one solution here, and it seems to be, based on intuition, the most ideal situation you can get. But this is where the real difficulty of the problem begins. How do you argue that there's no better solution? Right? Checking that this works is very easy to do so rigorously. Just plug in and it works. What I just described about how f can only come down faster and faster over time, and g can only go up slower and slower over time, and all these hand-wavy arguments is definitely not going to cut it for arguing that this is the best set of solution, right? So, without further ado, let us now take a look at how do we argue that this is the optimal solution in a rigorous way. To do this, I'm going to have to set up the scenario, and we are going to set up a situation that will allow us to prove by contradiction. So we are going to assume on the contrary that there is some f and g that gives a solution r less than pi over 2. Okay, to make our life easier, this f might have a few zeros, right? And without loss of generality, I can just take a look at the smallest positive 0 of f. Okay, yeah, since if there's already some r that is less than pi over 2, the smallest one will definitely be less than pi over 2 also. Now, sidetrack a bit, there might be some advanced viewers among the audience who would protest at the word smallest, because it could be the situation that the zeros of f have an accumulation point and it doesn't necessarily have a smallest, it only has an infimum. But worry not, because f here is differentiable, which means it's continuous. So the set of zeros form a closed set of the real numbers, which means that there is indeed a smallest positive 0. Now, if what I've just said in the past minute doesn't make sense to you, you can just ignore that. It's a small technical detail. But anyway, I'm going to just, without loss of generality, look at the smallest positive 0 of f. Okay. Now, what is the game plan we have in mind? The game plan is as follows. You might say, okay, I'm going to look at f positive, then f becomes 0. I'm going to figure out what is the fastest f can decrease, and so from here I can bound what is the smallest r needs to be. But that is a bit too weak for us to work, because we should use the fact that g starts at 0. So we want to also make use of g in the in our game plan. So the game plan actually is to look at g over f. So g over f starts off at 0, and eventually when we are at r, we get something over 0, which is infinity. So if we can show that the slope of g over f is bounded, is controlled by something above, then we can argue that there's a minimum time that needs to pass before I can reach infinity, so r needs to be of a certain minimum value. This sounds good as a game plan, except there's one small technical detail again that we need to address. Of course, something over 0 gives you infinity, right? No, actually, if you are unfortunate and get 0 over 0, you do not necessarily have infinity. So, in order to prevent this like obscure scenario from happening, I'm just going to play it safe and prove that it is not possible to have both f and g being 0 at the same time. Okay, so that this is indeed also, the goal here is indeed infinity. Okay, so to do this, I'm going to prove this claim that if I look at f squared plus g squared, it's going to be strictly positive for all x greater than or equal to 0. So hopefully I've motivated why we need to prove this claim. And proving this claim actually involves a very nifty little trick, which is not going to be easy to find, but let's take a look at what this trick is nonetheless. So basically the trick is I'm going to look at how fast d can decrease and form a lower bound. Because d starts off as positive, right? F squared plus g squared is positive. And I'm going to say, okay, d cannot decrease all the way to 0 by bounding the rate of the decrease of d. Actually, what I'm going to do is I'm going to look at ln of d instead. So by taking a look at ln of d, let's differentiate it and see how fast it can decrease. So I'm going to put in the absolute value so that I can do some inequalities later. Okay, so ln of d, if I differentiate, is just d prime over d, right? So d prime is 2f prime plus 2g prime, and then d is f squared plus g squared. So I can bring the absolute value sign in, and then mod f prime is less than or equal to g, mod g prime is less than or equal to f. So I have 4 mod f mod g over f squared plus g squared, and this is less than or equal to 2, which you can easily prove using either AMGM, or you can use your favorite move this over and complete the square, that kind of arguments. Anyway, this is less than or equal to 2, and what this means is that therefore ln d, its derivative is at least minus 2. So this is the key point. I want to show that d cannot decrease very fast. It will not decrease all the way to 0. So once I know ln d derivative is at least minus 2, I can solve the differential equation, and basically the ln gets moved over and get e to the minus 2x and so on. So the point here is, from here I can conclude that dx is bigger than or equal to e to the minus 2x d0, and d0 is positive, so dx is always strictly positive at all x greater than or equal to 0. Okay, so I hope this nifty little trick and sidetrack is it makes sense to you. It probably is worth like another 2 points in the out of 10, and most people might miss out this small technical point about the possibility of 0 over 0. Okay, so now that we established that indeed the goal is the start point is 0 and the goal is infinity, and we want to bound the rate of at which this ratio can increase. Actually, the easier way to deal with this problem is not to look at this ratio, but to look at arctangent of this ratio. So you might say, wow, this looks like a crazy contraption that you came up with out of nowhere. But actually, if you think about it, it's not too hard to motivate, because what is our optimal solution? Our optimal solution was f is sine, g is sine and f is cosine, which give you tangent. So arctangent of tangent is x, right? So this will tell you that, oh, actually this is something worth looking at. So over here, what we want to do instead is look at this function. It starts off at 0, it ends off at pi over 2, and I want to show that this function, the rate of increase is bounded above. We know at the back of our mind that the optimal solution will give hx equals to x here. So maybe this gives a very strong motivation that I just need to show that this slope here is bounded by 1. Okay, anyway, all that motivational talk aside, the solution now is define h as follows. Let us take a look at the rate at which h can increase. So I need to evaluate h prime, right? I'll just put in the absolute value so that I can do inequalities later. So h prime is just direct computing. You differentiate, when you differentiate arctan, you get 1 over 1 plus x squared, right? So I put the chain, by the chain rule, this giant ratio goes in here, and then I differentiate the ratio itself. So if I differentiate the ratio itself, is fg prime minus gf prime over f squared. So let's simplify this. The f square goes on top, and the bottom have f squared plus g squared. So the f squared cancel this f squared here. So I have fg prime minus gf prime over f squared plus g squared. Okay. And then now I bring the inequality in. My triangle inequality, I have mod f mod g prime plus mod g mod f prime over f squared plus g squared. Mod g prime is less than or equals to f. Mod f prime is less than or equal to g. So I have this thing is less than or equal to f squared plus g squared over f squared plus g squared, which is 1. So now you see everything coming together. H starts at 0. Okay? And when x equals r, the value of h is pi over 2. If r were to be less than pi over 2, then by mean value theorem, there must exist a point between 0 and r that has slope bigger than 1. But then this will contradict what we have just computed over here. So that is the end of the problem. So this is indeed a very unusual A3 problem because it involves some really like compact and powerful one-liner solution like this that takes a lot of preparatory work to set up rigorously, and then even coming up with this H to look at is definitely not an easy walk in the park. So I hope you found this problem interesting, but it's definitely an unusual problem to me. Yeah. So without further ado, let's take a look at yet another unusual problem. This time, problem A4. So for A4, we are going to let v1 to v12 be the unit vectors in R3 from the origin to the vertices of a regular icosahedron. So in case you don't know what an icosahedron looks like, it's basically this. And you might say, how would the contestants know this? Well, actually, this is the icon of the MAA or the organizers of Putnam. So on the question paper, there is actually this diagram already. Yeah, because it's the logo of the organizer. Okay, anyway, we need to show that for every vector v and every epsilon bigger than 0, there exist integers a1 to a12 such that by taking the integer linear combination of the vectors, I can get basically arbitrarily close to the target vector v. Okay, so this is the essence of the problem. I need to show that I can get arbitrarily close to the target vector just using integer linear combinations. Okay, so a couple of small things to make the solution rigorous. First, I need to tell you explicitly that actually without loss of generality, we can solve this problem for any desired orientation and scale of the icosahedron. So if we manage to solve this problem for one choice of orientation and scale of the icosahedron, we can solve for all orientation and scales, because basically for orientation, I'm just going to correspondingly rotate the vector v by performing the rotation that I performed to the icosahedron. I just perform the same to v, and then I solve the corresponding problem there, and then I bring the answers back. For scale, similarly, I can just rescale all my vectors as well as epsilon, solve the problem, the corresponding problem there, and bring the coefficients back. So basically the point is, I get the freedom to choose one orientation and scale of the icosahedron that works the best for me. Okay, we will need to use this later. Just keep that in mind. The other thing I need to establish upfront is this theorem that we are going to use, which is basically the crux of the whole problem. And it's actually not too difficult to motivate that you need to use this theorem, as long as you already know what the theorem is in the first place. You need to first know that this theorem exists, but it's quite easy to motivate that we will need to use this theorem. So the point is, what does this theorem say? The theorem says that if theta is an irrational number, then the collection of numbers n theta, where n is integer, is dense in the unit interval. And this theorem sort of makes sense, right? Because when theta is irrational and you keep taking multiples of it, it doesn't, when it looks, so this, by the way, this, I should say that this fraction thing is meant to indicate the fractional part of n theta. Apologies that it might be confused with the set notation. I meant to say like the fractional part of n theta. Anyway, this theorem sort of makes sense because if theta is irrational, then as you keep taking the multiples, right, it looks the fractional part sort of will not like repeat itself. You can imagine that it will distribute itself around the unit interval in a way that is dense. So I would say this is actually not too surprising, even though I will not cover the proof of this theorem in this video. Now we are going to rephrase this theorem in a way that will be more directly used in our proof. So this is just a direct rephrasing of the theorem. Let theta be irrational. Then given any alpha in 0 to 1 and epsilon greater than 0, there exists a k integer such that the fractional part of k theta minus alpha is less than epsilon. Basically, this is just a paraphrase of what the word dense means. Okay, so nothing much here. But I'm now going to further paraphrase this by not limiting ourselves to alpha being in 0, 1 and not limiting ourselves to looking at fractional parts. So basically, I now can say that given any real number alpha at epsilon greater than 0, there exist integers h and k such that k theta minus h minus alpha is less than epsilon. Basically, k theta minus h is going to capture the fractional part. And then, actually not just the fractional part, but alpha and k theta previously we are looking at just the parts in the unit interval. I'm going to take their integer parts and lump it into h. So this is actually the exact same statement as what we have before. Now, we are going to rephrase this yet again in a way that is going to be directly used for our problem. This time we are going to suppose lambda and eta are positive real numbers such that lambda over eta is irrational. Then given any real alpha and epsilon greater than 0, there exists h and k integers such that k lambda minus h eta minus alpha is less than epsilon. Basically, the way to prove this is very straightforward. You just divide by eta throughout. Then you will get k lambda over eta, which is irrational, minus h minus alpha over eta less than epsilon over eta. So basically what you do is you solve the problem with this theorem, but with alpha as alpha over eta and theta as, epsilon as epsilon over eta, and you take the values of k and h and you plug it back here. So then that would work. So this is the version that we'll be using in the proof of our theorem. Or rather the proof of the problem. Okay, so this means that we need to understand what these vectors are, and hopefully they sort of form irrational, they give us some irrational numbers to work with so that we can apply the conical approximation theorem. And indeed, one way of describing a regular icosahedron is to use the golden ratio. So it's actually a fact that there is a regular icosahedron whose vertices are basically using plus minus 5, plus minus 1, 0, and then taking cyclic permutations of this. So move the 0 over, 0 plus minus 5 plus minus 1, then move the plus minus 1 over, then get plus minus 1, 0 plus minus 5. And you can visualize it using this diagram over here. If this is the x-axis, the light green, and then the dark green where I'm showing now is the y-axis. and then the purple is the z-axis, then indeed you see that this point over here, this point will sort of be like 5, -1, and 0. Right? You see where this is going? Yeah, so this green plane is these 4 points. This dark green plane is x equals to 0, right? So it will be these 4 points, and then the purple plane is actually these 4 points. So if you don't know this obscure fact about icosahedron, I would say good luck to you. But if you know this problem, this obscure fact, right, it makes your life completely like trivial. So indeed, what you can do now is, if we focus on the x coordinate first, you combine the two light green points over here, right? You'll get 2, 5, 0, 0. And then at the same time, if you combine the two purple points, you'll get 2, 0, 0. So now I produce a integer combination of the vectors that is 2, 5, 0, 0, and another integer combination that's 2, 0, 0. And using the canonical approximation theorem, the ratio of this is 5, which is irrational. This means that there's an integer combination of these 4 vectors that differs from the x coordinate of v by any arbitrary epsilon that we want. We'll use epsilon over square root 3 over here. Then what we do is we repeat the same argument for y and v. And so now what we have is integer combinations of the various vectors such that the distance is actually less than epsilon away from v. So that is really all there is to this problem. So once again, this is a really weird problem where basically using this obscure fact about icosahedron and using the canonical approximation theorem, which is sort of, I wouldn't say it's too obscure, but you may or may not know of the theorem. Then these two theorems combined together just give a very trivial solution to the problem. So nonetheless, I hope you learned something about the icosahedron. Who knows, maybe this will be useful information for future contests. So that is all that we will be covering in this first video on this year's Putnam. If you enjoyed this video, check out our previous videos about the previous year's Putnam. Subscribe to the channel for upcoming videos on this year's Putnam, and see you soon.